In this video tutorial, I'll look at a static analysis of a 3D beam problem. It is a steel I-beam, and we will model it with a BEAM188 element type. The cross-section is straightforward. Flanges have a width of 100 millimeters, and total height is 200 millimeters. And both the flanges and the webs have 10 millimeter thickness. And the beam is 2 meters long with a force of 1000 Newton applied on the right hand and fully fixed to a wall on the left hand. We can create this beam model with a simple line, creating two key points and a line, and meshing the line with, say, so many divisions along the line, let's say 10 elements. And we will give the beam a cross-section property of area 3800 millimeters square. The second moment of area IYY is 22.9 10 to the power of 6 millimeter to the power of 4, height 200 millimeters. If we do a validation check for this beam problem, the stress at the root of the beam, the maximum stress due to the bending, can be calculated as my upon I, and that is our engineer's beam bending formula. So we know that the moment is 1000 newtons times 2000 millimeters, so that's 2 million Newton millimeters, and y is the distance from the neutral axis of the beam to the extreme fiber. So in this case it is half the height of 100 millimeters, and I is already calculated as the second moment of area here. So when these numbers are put in this equation, we need to get a bending stress of 8.723 megapascals for our beam bending problem. So we can compare this number with the numbers that we are going to get from our FEA. The help menu describes the BEAM188 element in detail. You can see the basis of this element, the theory, and also a description, for example, the I and J, two ends, and the K nodes that describe the orientation of this beam. The property of the beam is dependent on the shear modulus, area of the cross section, length of the member, and the flexural rigidity. So the formulation will calculate these, and a typical slenderness ratio calculation is done to make sure that the model that you are doing is representative of the beam theory being used as a basis of this element. For example, for a slender beam, when the slenderness ratio is high, you can see that the Timoshenko theory versus Euler-Bernoulli theory gives very close numbers. So you can use this beam for a relatively high slenderness ratio structure. One of the options that you are going to use is the key option 3, quadratic, and that means this beam element has an internal node, and that helps it achieve a better accuracy in representing the solution quantity along its length. There is even a higher option, a quadratic and a cubic option, and that gives two internal nodes with even better accuracy. The input data is described, the cross section is defined using a section type, and if you look at the element output definitions, you can see that we can extract data from the beam using the element table command. For example, the my, that bending moment on the beam, can be extracted from the database from SMISC for node I and node J values. So I'll demonstrate how to get these bending moments out of this beam using the etable command later. Okay, to model our beam, we will start using the preprocessor. First of all, defining the element type, we will add BEAM188, and we'll go to the options and define the element behavior as quadratic, so that gives it a bit more accuracy in representing the solutions as I just mentioned. So OK that and close that. So to define the cross section of that beam, we'll need to go under sections, beam, and common sections, and that brings up a beam tool. With the beam tool, we can choose a subtype of I-beam, and we can just give it a name as I-beam, and the values for W1, W2, and W3 are straightforward 100 millimeters, and W3 is 200 millimeters, and the thicknesses were 10 millimeters for the flanges and the web. Now, the beam tool allows us to define the cross-section accuracy. We can choose a fine beam or some sort of medium fineness. We can do a preview of that, and that shows you the cross-section. And if you do a mesh view, you can see how many integration points, etc. it is using on the cross-section. You can increase the fineness ratio, and that will give more and more subdivisions along the cross-section of the beam. So if we accept this version, we can define our geometry in terms of the length of that beam, 2 meter length. First of all though, let's define our material model, and we'll define a structural, linear, elastic, isotropic material model, and the material is steel, so let's define 207,000 for Young's modulus and 0.3 for the Poisson's ratio PRXY. So OK that, and we can close the material, and the next part is defining the length of the beam. So to do that, we'll create a couple of key points. The first key point is at key point 1, location 0, 0, 0 at the global Cartesian coordinate system, and key point 2 is at x 2000 meters, 2 meters. So if we do OK that, and we can create a line that connects the two. So we can do that modeling, create lines and a straight line, and we need to choose 2 key points for that, key point 1 and 2, and press OK. Now the difference between this model and the frame problem we studied earlier was that frame problem was a direct model generation. We were creating the nodes and elements directly. In this case, for this beam example, we are creating a solid model entity, which is a line formed by 2 key points and a line, and we will mesh this line with the beam elements of type BEAM188. So next part is to define how many divisions do I want on this. We can do that under meshing and under size controls, manual size, lines, and picked lines. I can pick this line and say, on this line I want, let's say, 10 divisions. So it will create 10 beam elements along the length of this line, and press OK. So you can see that the continuous line is turned into a dashed line. That doesn't mean that the beam is meshed, it just shows how many divisions it's creating along that line. Another important point regarding the beam elements is that they need to be oriented in space using an orientation key point. So we can create a separate key point that is not attached to this line and use that in our line attributes. So we can do that under modeling, create key points in active coordinate system. So that will be our third key point 3, and let's say somehow in x 0 and y is, let's say, a couple of 100 millimeters. So it's just another key point on the y-axis effectively, and that will define the orientation of the beam elements that we are going to create. So that orientation is done under mesh attributes. So under meshing, mesh attributes, picked lines, I can pick this line and click OK, and I can say that that line will be meshed with material 1 of type BEAM188 and cross-sectional property of I-beam, and this box is checked so that an orientation key point can be picked. So if I click OK, it'll ask me to pick an orientation key point. I'll select key point 3 and press OK. So I can go and plot lines. So the line is still there. I need to now mesh this line with beam elements. I can use my mesh tool for that. I can then click on mesh and select the line and click OK. So this shows a simple continuous blue line, so that's not very descriptive because it's a line element. It's not easy to see what the orientation etc. is. So even if I rotate this in 3D, it's still a line. It doesn't show the cross-sectional property unless I go to plot controls and go to style, size and shape, and turn on the element shape display. So if that is turned on, that is the /e shape command, press OK, you can now see the cross-sectional property imposed on that line. So that orientation key point we created here on the y-axis oriented this I-beam so that the cross-section is defined as such on the YZ plane. So that are these are the beam elements, the 10 beam elements, and you can also see in the cross-section of it how the section is defined, the mesh view of the section. And remember, this is still representing a 3D structure, but the basis of it is a simple line. So the complexity is somehow hidden. The elements are far more complex in the theory being used behind it. So that's the geometry done, and the next bit is to create our solution. So to do that, we can apply some loads. Analysis type is going to be static by default. We can define loads and apply structural displacements on key points. rather than applying the loads and displacements on nodes, in this example we've defined solid model entities like key points and lines, and we can create a mesh on that line. So when we fix this key point, that boundary condition is going to be transferred on the underlying node. So if we pick that key point and fix all degrees of freedom, and remember in beam element types you got translations as well as rotations, 6 degrees of freedom per node. So that value is going to be 0, and press OK. So you can see the blue arrows and orange arrows representing the fixing of the rotational degrees of freedom as well in all 3 axes. And we'll need to apply a load on this as well. So we can go to apply structural force moment on key points. If we select this key point, we want to apply the load on the negative y-axis so that it is going in the right direction. We can change this to Fy, and the negative value will mean that it is going down the way. So press OK on that one. So you can see that the red arrow is pointing in the right direction. So these are the boundary conditions defined, and we can create our solution. We can do that under solve, current load step. It gives us a summary. Click OK, and takes a second to solve. Close this and close this button as well. We can now look at our results. On the results summary, there's still only one set of data. We can go and read this first set and can start plotting the results. First of all, the deformed shape. Deformed and undeformed shape together looks like this, and we can create a nice animation of that, of the deformed shape, and we can see that it is going the right direction. That's fine. We can stop this, close, and the next is to look at stresses. We can plot contour plot of nodal solution, stress, x component. Because I'm plotting the elements in a 3D representation, remember, these are line elements, but on the 3D representation it still manages to calculate the bending stresses accurately. So these are my bending stresses, so in the direction of these elements. So therefore the 8.72 value at the top and negative 8.7 at the bottom of the element, these are as I expected in the engineer's beam bending formula. The other thing I mentioned was to extract data from the database. So that means we create element tables, define a table, add, and we need to use, say, sequence numbers, and we can define MYI for the moments, beam bending moments for the first node of each element, and that's under SMISC2, and then apply that. At the second node J of each element, that will be MYJ, and by sequence number SMISC15, and press OK. So we got MYI and MYJ moments on the beam elements stored on the table, and we can now plot them. And we can plot these using plot results, contour plot, line element results. So the first node I, is MYI, and node 2 MYJ is used, and we can plot it on under undeformed or deformed shape, etc. So let's choose this, and then we can see how the bending moment changes from the root of the beam to the tip of the beam. If we view the front, probably that looks better. So the bending moment diagram on that structure is at the root of the beam. We are getting a bending moment of 2 million Newton millimeters as we expected. Using similar tables, we can get shear force plots and bending moment plots in different axes, etc. So this effectively concludes the beam element interactive analysis. But however, you can still use a log file to represent this structure. We can have a simple notepad log file definition of this whole problem. This log file starts with a clear command, so it clears the database. So we can simply copy this into this window, and then that means I'm starting fresh in my model. The rest of the commands are simply running the preprocessor commands, like ET defines the element type as BEAM188, key option defines the quadratic function for the beam type, and section property defines the cross section as for the I-beam. The material property MP is defining the Young's modulus and Poisson ratio. The key points are defining the geometry. Line is from key points 1 to 2. AD size simply says that there are 10 divisions along this first line. L attribute command says that there is key point 3 defining the orientation, which is linked to this key point 3, and L mesh simply mesh this line. E shape turns on the element shape, so we can view these line elements as if they are 3D. Then the solution commands, we choose static analysis type, fix key point 1 in all directions, apply a force of -1000 in the Fy direction, and solve this. And in the post processor, we can first set the first result set and plot displacements. We can create tables representing the bending moment and then plot these as line element results using the PLLS command. And the PLNSOL simply plots the nodal stresses on the elements. So we can say change anything on this log file and then rerun it. For example, if we want to change the cross section, we can do that simply changing this number and copy this section and then paste into our input window and then rerun it. And that shows us our elements, and we can view this as an isometric view, and we can continue to the solution and copy and paste. So that's creating the solution and displaced shape. So this smaller cross-sectional beam has a bit larger displacement. So we can close this. So the log file option gives a good simple interface to the model itself. And this concludes our tutorial on the beam problem.